Hello everyone, my name is Henry. I am a software engineer at Meta, and for the past 3 years, I have been working on trusted execution environments. So today, I will be talking about some of the TEE work that we've been doing at Meta, specifically to use SGX Enclaves to secure our edge services. I will discuss some of the challenges and trade-offs that we encountered when working with SGX applications. So I think most people here may be familiar with SGX, so I will just gloss over the overview, but I wanted to talk about some key limitations of working with it as a developer. So building, deploying, and interacting with SGX Enclaves is similar to using dynamic loaded libraries. However, SGX development is known to be quite tricky and restrictive for these reasons. So the Enclave interface is defined by these edge routines. Enclave calls transition execution into the Enclave and execute a trusted routine. Out calls are invoked from within the Enclave and execute a routine on the host process. Edge routines also have significant runtime overheads. CPU cycles are spent saving and restoring context. This is similar to system call context switches. There's also latency for data transfer, serializing and copying data buffers across the boundary. The format of data transfer is also quite restricted. The edge routines have a C interface, so that means you can't pass C++ objects. For example, you can't just pass a pointer to a C++ object and then dereference it across the boundary because of ABI incompatibilities. And lastly, enclaves are statically linked with a custom libc. So usually this is the one provided by Intel's SDK, or maybe another one depending on what platform you're using. So the problem here is that this libc is a small subset of the standard libc API, which means that many symbols and syscalls are undefined. And this is problematic when you try to port code to be built and run inside the enclave. So this is where a platform might come in handy. FBEnclave is Meta's platform for onboarding our services to use SGX. Now, before my time, other open source platforms were explored, for example, Silo or Graphene or Grameen SGX, Scone. These platforms sought to run entire applications inside the enclave, ideally without modification to the source code. But ultimately, we decided that these platforms were not very compatible with our internal build infrastructure, so we decided to create our own. And in fact, the Grameen platform is sort of what we're trying to emulate as well. So FBEnclave mostly abstracts the low-level SGX build dependencies like the SDK and the various other tools that come with it. But most importantly, it integrates with Meta's internal build system. And for context at Meta, all the software teams use this common set of build systems and build infrastructure, which is partly what lets us move fast. So this enabled us to leverage other build components or infrastructures like continuous testing, building, deployment, and packaging, saving us a lot of time from reinventing these components. Another key objective was to support these common libraries like Folly and Thrift inside the enclave. So these are open source libraries that are used widely by Meta's services. Folly is a general utility library, and Thrift is our main serialization and RPC framework. So to make this happen, we had to enable a lot of code to compile inside the enclave because these libraries are quite large. So we did this by supporting more syscalls. We implemented the proxy functions that serialize inputs, outputs, and do the ocalls that actually invoke the syscalls. We also maintained this custom libc that's kind of a Frankenstein libc of, and it implements the missing symbols that you might need. And this is to make it more compatible with the libc versions used at Meta. And compatibility is a big issue because if your code is written with the assumption of one libc version and you try to port it over to another one, there might be build time and runtime issues. So the initial use case for SGX was to harden Meta's edge services from certain physical attacks. Even though SGX provides protection against some privileged software attacks, Meta relies on other mechanisms to provide defense in depth and to safeguard access to production. So Meta maintains POPs around the world. We refer to this as the edge network. And some edge services operate with high-value secrets. And these high-value secrets must be deployed to process memory. This is because it may be an unacceptable performance trade-off or latency hits if we were to offload these operations to a remote but more secure data center. So the problem here is that these edge POPs may reside in physical locations not owned by Meta. So there is more inherent risk of physical access, so more risk of physical-based attacks that exfiltrate secrets. So the candidate service that we wanted to harden with SGX is called the TLS offload service. This is a companion service that is deployed alongside ProxyGen. ProxyGen is our HTTPS reverse proxy. It terminates incoming TLS connections from clients wishing to connect to our domains like facebook.com, instagram.com. During the TLS handshake, ProxyGen will then offload the signing request to the offload service, which is provisioned ahead of time with the TLS keys. So the reason why this architecture is like this is to mitigate the Heartbleed attacks back in the day by moving the private key material out of the external-facing ProxyGen process memory. And then in 2018, we conceived the idea of moving these private keys and signing operations into an enclave. And finally, this past year, with the rollout of SGX-capable hosts across our edge fleet, we now have widespread deployment of SGX-hardened offload service. And this was a big deal because this is Meta's first deployment of SGX Enclaves to a high criticality production service that serves thousands of requests per second. So I spent about half a year transitioning the offload service to use SGX. This work was mostly around refactoring the code and extracting the enclave-specific logic. So we explored two partition methods. First, putting the thrift server inside the enclave versus putting it outside the enclave. And for context, the thrift server, it basically encapsulates a socket. It has CPU and I/O thread pools. It handles incoming requests and delegates the workload to some worker thread. So as I mentioned, the initial objective of FBEnclave was to try to run entire applications inside the enclave. So this was naturally the first thing we tried. But we realized that the common service libraries used at Meta, they are very large, and they are not written with enclaves in mind. They pull a lot of other first-party and third-party dependencies. And we will see how all this incompatible code causes a lot of issues down the line. So since not all code compiles inside the enclave, we have to do some tricks to make it work. One is by patching this custom libc, we can add these missing symbols and syscalls, but maintaining this custom libc gets very tricky because it's quite a large library for a small team to handle. Or we can do these ocalls to execute the problem code outside the enclave, but this is also not a very scalable or neat solution. It causes these convoluted code paths. Sometimes execution transitions several times across the enclave boundary. So performance was also poor because a service owner might not have control over the hundreds of other common libraries that they depend on. They would not be able to control the syscalls that are invoked. And syscalls, as I mentioned, are not natively supported, so they require ocalls, which degrade performance. Build reliability was also a huge issue. It was a daily occurrence for us to investigate and fix build breakages that would happen. And this happens because at Meta, we use a monorepo. So every day, there are thousands of commits that land that impact all of the shared libraries and our build system. So the main benefit from all this is that we can have TLS of the incoming RPCs terminate inside the enclave. And this is really useful for some services that may accept or give out secrets. It basically creates this end-to-end encrypted channel that terminates inside the enclave, and you don't need an application-level encryption channel to be established. So this implementation did not work out very well for us. It was quite hard to maintain. So we ended up exploring putting the thrift server outside the enclave and doing an eCall to transition into the enclave to do the signing operation. So the code was much simpler inside the enclave. The only dependency we really needed was OpenSSL to do the signing operations. Performance was also much better because there were no random syscalls invoked by hundreds of libraries that we accidentally pulled in. In fact, there were no O-calls at all, so we only had the one main E-call that did the signing operation. Build reliability was also much better because with less code you have, the less chances of something going wrong. So the main downside, or maybe downside here, is that the TLS for incoming RPCs terminate outside the enclave. But for our particular use case, for the offload service, this was actually perfectly fine because the inputs and outputs of the offload service are not secrets. They are just hashes and signatures. So this was the implementation that we ended up deploying, and for the past few months, it's been running with minimal maintenance overhead. So security does not come for free. There's a little bit of performance trade-off. Back in the day, we did these micro benchmarks to look at the SGX operations, specifically edge routines, and we compared them to syscalls, for example. So this experiment just shows the base transition latency. It doesn't account for any of the data transfer that may happen. There's no business logic. It's just a no-op. So the only takeaway here is that edge routines take an order of magnitude longer than the syscall. And I did this in cycles at first, but then I converted it to microseconds for this table. So as for the offload service, our production engineers cared about these metrics: capacity, request handler latency, and CPU util, which are all tightly coupled. So this graph over here on the left side shows the request handler latency, or the average of it for this particular service. And we can see that the gap is roughly 40 microseconds, depending on the workload. We attribute this latency gap to the edge routine, the main edge routine that is invoked. So some time is spent transferring data in and out, maybe in the order of 100 bytes. The CPU util was also measured to be maybe 0.01% overhead, which we thought was not significant because 100% means that the process is using all CPU on the host. So overall, we thought these overheads are not significant enough to block the deployment of SGX enclaves for this offload service. As for future work, so even though SGX was the initial trusted execution technology we worked on, we knew that there would be upcoming ones. So this past year, we actually worked on a platform to deploy services running in confidential virtual machines, and this is backed by AMD SCV, SMP. The main trade-off here compared to SGX is that we would no longer have to refactor the application code, which could be pretty painful. But the TCP is much bigger now because it includes entire operating system. So in the future, we also foresee extending our platform to support Intel TDX. Thank you. That is all. Oh, is my... I have 7 minutes of questions, apparently. Yeah. Yes, question here.
Yeah, I saw in your slides there is latency.
Oh, yeah, I can...
Is the SGX one is higher, right? Oh.
Yeah, it's overhead. So I forgot what color it was supposed to be. Sorry, this thing is not working yet, but... Yeah, did I get it mixed up? I might have got the labels mixed up here, but yeah, the blue one says regular. Okay, yeah, I got the labels mixed up, but it's an overhead, so it costs more. Yeah.
Another thing is that you mentioned that the use case is actually for, like, if we don't do this in edge, there will be some kind of latency